Okay, this was where we stopped. So we are specifying this polynomial, and we are saying that this polynomial is given by this, where this polynomial is what you have two of the roots of that original polynomial we started with, which is a, is given. So b has two roots. Know that this is a fifth order polynomial, so it has 5 roots, and we are specifying b as the two of the 5 roots of this is this, which is 1 and 0.5. So after specifying it, there's a MATLAB function called the conv. So what the conv does is that it's going to divide this polynomial. Remember, this polynomial is the a we have here, then b, this polynomial we just specified. So it's going to divide this by this, and it's going to store the result of the division in D, and it's going to store the remainder in A. So when we call this function, it's going to give us D. So D is the result of dividing this by this, and is giving us this polynomial, which is a third order polynomial, and this is the remainder or the quotient. So since this b is one of the roots of a, so definitely there's no remainder. So this is how you specify it. In order to, like I said, if you want to know how a function works, I say up the conv. Say we want to know how this function is in MATLAB. So MATLAB will bring up a documentation, and it becomes vector A out of vector B. So um, it divides this function by this function. Then this is the result, and this is the remainder. So Q is the quotient, then R is the remainder. Then MATLAB has a function that you can just directly find the root of a polynomial. So if we want to get the root of D, you know that this is another polynomial, it's a third order polynomial. If you want to get the root of this polynomial, you just call the root function, and it's going to give us the root of the polynomial. Then if we want to multiply a polynomial by another polynomial, for instance, we want to multiply this D polynomial by B polynomial. So when we do that, we can use the conv function. The conv function is going to multiply it. And when we do the multiplication, it's giving us the value of the original polynomial. And that's because this is D is one of the, this D is the one polynomial, is a third order polynomial, and this is a second order polynomial. And this D and B, they are both roots of the polynomial A. So when we multiplied it together, we got the original polynomial. And if you want to directly calculate the root of A, that was the original A we started with, the original polynomial we started with. So this is our A. We started with this, and you want to get the root of the polynomial. Simply say root A, and MATLAB is going to directly give you the root. If you want to know how the function works, you can just say up root, and MATLAB is going to pull out the documentation of actually getting the roots of the function. So it's saying that root r is equal to root object. It returns the root of entry object. Then if we want to get the, because R now specifies the root. So if you want to build up the polynomial from the root, you use the poly function. So the poly function, we just multiply all of this because R is all of this. And when we do that, we are going to get the original equation. So this is the way MATLAB is able to help us to calculate the roots. So we needed to know how these functions work in MATLAB, and you needed also to know the method that MATLAB uses in order to find the root. Like for the F0, which is like the main function for getting the roots of specific functions, it uses some of the methods we've considered in the previous two classes, the interpolation method and the bisection method. And let me go back to the notes. So we are going to do a case study. So we want to solve a practical problem, and want to use the numerical method we've considered, which is the root. So this is an electric circuit. It has a resistor, an inductor, and a capacitor. So we want to solve or want to design this electric circuit using our new knowledge of the roots of equation. And now we know from Kirchhoff's second voltage law that we need to sum up the voltages in each of the individual elements. So the voltage across the resistor is given by IR, and the voltage across the inductor, L, is given by L I dt. Then the voltage across the capacitor is given by Q divided by C. So we use Kirchhoff's second voltage law, that the algebraic sum of the voltage drop in a closed circuit is 0. So we sum up the voltages in the circuit, and is equal to 0. Then we know that the current is equal to the rate of change of the charge with time. And using replacing I with Q, the T, we arrive at, so when I is replaced by the Q, the T, you arrive at this. And when you solve this second order differential equation, you would arrive at this. So you can use integration. So you can use integration to solve it, or you can use Laplace to solve it. So when you solve this, you are going to arrive at this, and this is the initial condition by which we arrive at the exact solution for this particular differential equation. Then the question is that we want to find the value of R being the resistance that gives us an inductance of 5, a capacitance of 10 minus 4 farad, and a charge dissipation of 1%. So Q divided by Q naught is 0.01 at a time of 0.05 seconds. So we want to find R now. So what we are going to do now is that we are going to put in all these values into this equation. And before we actually put it into the equation, because we want to solve for R, we want to get the resistance that is going to give us these values of time, inductance, capacitance, and percentage charge dissipation. And in order to do that, we're going to reduce this problem to finding the root. So remember in the first lecture on root, I told you that you can reduce any equation to finding the root by actually equating that expression or that function to 0. So we are going to equate this function to 0. So all we are going to do is that we're going to divide both sides by Q naught. Then after that, we are going to bring this q divided by q naught to the other side. And we're going to evaluate the function at, we're going to evaluate the function when is equal to 0. So we know the values of everything. We know time, we know the inductance, we know the capacitance, and we know the time, and we know the percentage charge dissipation. So we know all of this, but all we need is R. All we need is the resistance. So we would equate the problem to finding the roots of the equation. So I told you that all you need to do is divide both sides by Q naught, then bring Q divided by Q naught to the other side, then equate it to 0. So we've reduced the problem to finding the evaluating f of r when r is equal to, we want to evaluate r, sorry, when f of r is equal to 0. So the points at which this expression or this function is equal to 0 will give us the resistance we are looking for. And now when we put in all the values, like we have everything, we know the time. The time is 0.05 seconds. We know the inductance, we know the capacitance. So we are just going to put in all the values into this equation. And we know the the charge percent dissipation, and is 1%, which is 0.01. And now we've reduced it to finding the roots of the equation. So now we want to find the root of this equation, but we are not giving an initial guess. So like I told you previously, you're going to use Excel, or you're going to use a graph to actually give us the value of the initial guess. So if you're not giving the initial guess, you would plot the function at different values of r, so that you can have an approximation of where the root is. Then you can use other methods, the other method we've discussed to solve it. So now we want to evaluate this expression at different values of r, then we'll plot it. For this, we are going to use r from 0 to 400 or 420. And the reason why we are doing that is because this square root, we don't want it to be a negative number, because if it is a negative number, then we're going to have an imaginary component, which we don't want. So the r we're going to choose, so if you say r is equal to 400, which is the maximum we are stopping, so 0.01 times 400 squared will give us like 1,600. Then 2,000 minus 1,600 is still a real number. It's still a positive number, sorry. So you're going to choose R between 0 and 400. And the reason why we are choosing it between this 0 and 400 is that we don't want this evaluation to give us negative. Because if it's negative, then we'll be having an imaginary, a complex number. So we are going to use Excel now. So we are going to write this particular equation in Excel, because we want to use Excel to plot. We want to use Excel to plot the graph for us. And when we do that, this is the evaluation in Excel. So there's a R here and there's a R here. So exponential. So this is how you represent exponential in Excel. Minus 0.005 times R, which is this. Then cos. Then there's a square root. This is the square root. So this is SQRT. 2,000 minus 0.01 multiplied by R squared. So this is the R squared. then times 0.05, then minus 0.01. So let's go back to Excel. So we are now in Excel and want to plot the function from 0 to, we chose R from 0 to 440. So here, you're simply going to, this is the expression in Excel format, and we evaluate it. Then for every one of them, we're going to evaluate it. So if I had chosen, remember I was telling you that the values of R should be between 0 and 400, or 440 is also okay. If I had used, let me extend it, it's giving me not a number, and that's because it's becoming imaginary. This square root is giving an imaginary component. So that's why it's giving me not a number. So I just decided I will just stop at 440. So when we plot the graph, remember I told you previously that if you are not giving an initial guess, then you have to plot it so that you would have a an idea of where the guess is. So let me try to format my axis. Let me say 460, and let me say 20, and okay. So I formatted my axis, and so this is the graph is giving me. So remember that we know that the root of the equation is when the curve touches the x-axis, and we know that, okay, it touched the x-axis around this point, but we are not sure of the point exactly. But from what we know that the root should be between 320 and 340, because it's in between 320 and 340 that it crossed the x-axis. So we are going to use our initial guess as the lower limit is 320, and we choose a upper limit as 340. So let's go back to another sheet. So we're going to choose our lower limit as 320 and our upper limit as 340. So we want to find the root. I want to use a method. So I'm going to use the bisection method. So remember that you need to specify the estimated error. So let me choose the estimated error is 0.001. So I want it to evaluate the root with an estimated error less than or equal to 0.01. Then the maximum number of iterations I want it to go is 100. So as we normally do, after specifying it, we go to formulas, then create from selection left row. Then okay, so Excel knows that XL is 320, XU is 340, ES is 0.001, and IMAX is 100. So now we're going to write, we're going to use the bisection method in order to calculate the root. So we go to Visual Basic Excel, and we are now in Visual Basic. So we've already considered the bisection method. So this, I've explained it in the first lecture of finding the roots of an equation. The only thing you need to do is to evaluate is another function. This is the function we are evaluating because it's a different question. So depending on the question, this function is going to be the same thing, but the bisect function is going to be the same thing, but the function, depending on the question, this is going to be different. So we're evaluating this function. So we have to change this function to the question in which we arrived at. And this is the this is the bisection method. So when I go back to the Excel worksheet, I will just call the method because I've already written it. And the way we call it is equal to bisect because that's the name of the function. XL, the lower limit, XU, the upper limit, ES, the estimated error, then Imax is the maximum number of iterations. And Excel was able to give us this value. So this is the value of the resistor or the resistance that gives us, that solves that particular circuit we are dealing with. So if we want to know at which iteration we got this value, remember we specified 100th iteration. But I'm sure Excel did not get to the 100 iteration because we said that let the estimated error be less than 0.01 or the maximum number of iterations be 100. So let's look at the iterations at which Excel VBA went through in order to get to this particular value. So in order to do that, this is where we're going to put the iterations. So we're going to call the bisect method the same way we called it, but in this case, XL, XU, then ES, then so in place of the maximum number of iterations, we are going to put H1 so that it's going to come to this particular box or cell. So we're going to put H1. It says it's going to evaluate the bisect method at the first iteration. So this is how it was able to evaluate it. Then at the second, third, fourth, then up to the, I stopped at, it's supposed to be 25. I stopped at 25. So these were the iterations the VBA code went through in order to get to the to this value. So it got to this particular value, I think, at this particular the 16th iteration. So because at this particular 16th iteration, the error is less than 0.0001. Let me try to increase the accuracy. Okay, so I've increased the accuracy, and the we have a much more accurate estimate of the root. So let me go back to the note. So now we used a practical example in order we designed an electric circuit, then we calculate the value of the resistance R that is able to produce these values, that is able to produce a charge dissipation of 0.01 at a time of 0.05 with an inductance of 5 Henry and with a capacitance of 10 minus 4 farad. So this wraps up our conclusion for finding the roots of equations. So we started with so I'm summarizing now. So after that, we just close the class for today. So we started with the with the bracketing methods, like the bisect method and the bisection method and the first position method. So you can, when trying to, let me share my Excel screen. So when trying to just go over it, you can just write the first position method and solve it this particular electric circuit and try to see the results. Then we also use the open method. So we talked about the Newton-Raphson's method, the single fixed point iteration, and the last method, which is the second method. So you can try to use all these methods for the case study we've just considered. So this class marks the end of our consideration on finding the roots of equations. So be on the lookout on Moodle. I'll be giving an assignment based on this. Then at the next class, next week, hopefully, we are going to start another topic, which is optimization. So optimization is similar, or is almost the same thing with the roots. It's just that for the roots, you are trying to find the zero of the function. So you want to evaluate, you want to find the value of x or the variable when the function is equal to 0. But for optimization, you want to get the maximum or the minimum value of the function. So is practically the same thing with finding the roots of the equation. So thank you everyone for joining. If there are no questions, then